Well, hello everyone. A while ago I had a video and I said that if you use an induction motor with a variable frequency drive, there is a way that you can make that induction motor output more torque than it's supposed to. Well, thing is, see, that's really easy to say, but if I can't prove it to you, some of you guys probably aren't going to believe me. So today I'm going to show you how you can test the stall torque of an induction motor that's hooked to a variable frequency drive. And you can do this without using any expensive tools. Like, we don't need a strain gauge or a dynamometer. I'm going to show you how to do this in a really simple way. Now I'll be using the same induction motor as I did before. So this is a 3/4 horsepower, 3-phase 6-pole motor. So it's rated at 1140 RPM at 60 Hertz. So we're expecting this motor to produce about 3.5 pounds-feet of torque normally. So that's what it's rated for out of the factory. Okay, so you see this here, this is a motor and this is a pulley that fits on the motor. So what I've done, I've drilled 2 holes in it and I've put 2 cap screws in it. And this bar has a hole in it here and there's a steel cable connected to it. Don't know if you can see that right here. So the distance between the center of this pulley here and where this steel cable is, that's 1 foot. So I want to measure in pounds-feet of torque, so we have to have 1 foot there. Okay, so at the other end of the cable, there's a weight. There's a threaded rod connected at the other end so it doesn't come loose. See? That's 15 pounds. So if the motor can lift this, then it should be outputting at least a stall torque of 15 pounds-feet, because it has the bar the 1 foot distance. Now in order to make this happen, we do need a variable frequency drive. So I'll be using this one. This is a Yaskawa Magnatech GPD 505 drive. So this drive can output up to 460 volts, up to 400 Hertz, and up to about 21 amps, maybe 150% overload. But the reason is, see, induction motors produce peak torque usually between something like 3 and 4 Hertz of slip. So even if you had 3-phase power, if you just hooked the motor directly online, it wouldn't make peak torque at stall because that would be 60 Hertz slip. So the motor would be standing still, then you'd be feeding it 60 Hertz. That's way too much. So we need to bring the frequency down. So what I'm going to do is I'm going to set this drive to output 4 Hertz and the voltage. That's the next important thing. So we need to have peak voltage much lower. So the drive, most of them normally they output 460 volts at 60 Hertz, or if you've got a 230 model, they'll output 230 volts at 60 Hertz. So you need peak voltage much lower. So I've told the drive I want peak voltage at 20 Hertz. So the motor's going to be receiving a lot more voltage than it normally should. So it's going to increase the flux inside the motor, it's going to make those magnetic fields stronger, and it should allow us to pick up the weight. Now of course, some of you guys are going to pick up on this and you're going to say, won't that make the motor very hot? And the answer is yes, it will. So if you plan on doing this continuously, which I don't recommend you do, you will need some heavy-duty form of cooling. Now normally I do have a fan on the back of that motor blowing air into it for my tests, but I'm not going to run it because this is going to be way too loud and you won't really be able to hear anything. It's just annoying. So enough talking, now we're going to try it. Oh, one other thing before we go on. As you note, this motor is clamped here to the table. You need to have your motor securely fastened, otherwise the counter torque is just going to spin it over. And on the other end of the table, you can't see it, but I do have counterweights on there so it doesn't flip the whole table over. Yeah, that has almost happened. Okay, so the motor controller is on. You can probably hear the fans. So what I'm going to do is I'm just going to flip the switch on. I don't want to do too many tests because it will just heat the motor up. And you guys watch and you tell me if that little motor lifted that 15-pound weight. So I think it lifted it a little bit. It didn't really manage to spin it all the way over, but that's okay. I don't really want to be hit by a flying weight anyways. So it did manage to pick up 15 pounds, so I think it did produce at least 15 pounds-feet of stall torque anyway. Okay, so as we saw, it clearly did it, but as I said, I don't think this would work continuously. Maybe if it were internally oil-cooled. So this motor was wired in delta, so that's the lower voltage winding. It's 220, it's got a 440 and a 220 winding, so this was in delta, so it was in 220. So that's normally rated for 3.2 amps. But in order to make this happen, we had to push through, I don't know how many volts, it was pretty high. Let's say, I can't think off the top of my head, I think it was 192 volts. And you'll figure it out. I think it was 192 volts and 21 amps. So yeah, that's quite a bit higher than the motor is normally rated to accept. But it did manage to make a little bit more than 4 times this normal rated torque. But like I said, it's going to get really, really hot. You have to have some kind of cooling system if you want to do it continuously. But it does at least show us that these induction motors are capable, given the proper inputs. So, I thank you guys for watching, and I probably am going to try to make some more videos soon. I know I keep saying that, but you know, things get busy. So if you do have any questions, I'll try to get to them. You can comment or message. And I'll see you guys later.